Hey everybody, today we are going through the final part of the final exam review. We are going through problems 27 through 40. Now right off the bat, if you look at number 27, I have already added in a diagram of how a normal distribution works. So hopefully that will help us get the job done here, starting with 27, and then we will move on to a little bit about surveying and biased and unbiased samples, and we'll just go on from there. So we'll start with 27. What percentage is within 3 standard deviations of the mean? All right, so let's say the class average on a test was a 70%, the mean was a 70, and the standard deviation was 10. That means you'd have 60%, 50%, 40%, that sort of thing, okay? But in this case, that doesn't really matter. They just want the percentage breakdown. So within 3 standard deviations of the mean, that means anybody from here to here. Now, we all know that about 0.5% of the population is below 3 standard deviations, and about 0.5% of the population is above. They get kind of left out of the deal. But we also know that the other 99% fit in within 3 standard deviations. All right. Next, greater than 2 standard deviations below the mean. So 2 standard deviations below the mean would be right here. So we don't want them. We want only the people greater than that. So we don't want that 0.5%, we don't want that 2%, but we want everybody else. The fastest way to get that answer would just be to do 100% and then take away the 2.5%. So 100 minus 2.5, there you go, 97.5. So 97.5% of the population would be past that. All right. Less than 1 standard deviation below the mean. So now we're going to go to 1 standard deviation below the mean, and I want anything less than that. Now I'm just going to mess with this real quick. Basically, I want that, or the 0.5%. Anything in orange would pretty much count. So that means I want the 13.5, I want the 2, and I want the 0.5. Anything less than 1 standard deviation below the mean. So that would give you, and I think you can probably do this in your head, but I'm just trying to demonstrate, that would give you 16%. The answer to the next question is 16%. And last but not least, between 1 below and 2 above. So I'll do that one in blue. Basically, that means I want here, here, and here. So 34 plus 34 plus 13.5. Anything in blue counts. Anything from 1 below to 2 above. So the answer is 81.5%. All right, next, there's a lot of reading on 28, but I believe that you can probably do it. Let's see. So all the freshmen are doing an orientation, and the principal is going to ask 25 random freshmen what they think. So is that biased or unbiased? So I would say the first one is unbiased. And the reason why is that the principal chose 25 random students from the population. Now pay attention, because B is definitely going to be biased. Let's talk about it. The members of the school drama club want to know how much students are willing to pay for a ticket, and each member of the drama club is going to ask 5 of his or her friends what they are each willing to pay. Well, of course that's biased, because if you are a friend of someone in drama club, you would probably be willing to pay more than someone else would. That's my opinion. I mean, some of these can be a little bit subjective, but I feel like those are pretty good explanations. The first one was a random sample of everybody. But the second one wasn't, because obviously you're going to be more likely to support your friend. Okay, all right, now we're talking about a coffee shop, and the coffee shop is considering changing the menu, but they want to know what people think. So let's explain. What would a convenience sample look like? That would be like handing out surveys, or maybe like a QR code, and having people volunteer to fill out the survey. That's convenience. You're basically just saying, hey, if you want to fill this out, would you please fill this out? You're not really going over a way of randomly picking people. You're really just saying, hey, would you like to fill this out? Please fill this out. Now, the reason I wouldn't think that would be the best way to go is because you're not really getting a random sample. You're only getting the people who are willing to take the time to fill it out. And those people may be more biased either one way or another. Maybe they love your coffee shop exactly how it is. That's why they go there every day. And maybe they don't want you to change. Or maybe it's going to be somebody who's just passionate about how much they don't like your coffee. Although, then why are they there? That seems kind of weird. All right, systematic. To have a system would be like choosing every nth person. Now remember, nth could be like every fourth person, like alternating every fifth person, every 10th person, and asking them their opinion. But it has to be a system. I've got a system. I've got a rule. This is how I'm going to choose people. Okay? That would be an example of a systematic sample. And simple random is usually, I would say that would be like a computer-generated kind of thing, where you have like a list of people who signed up for your club, and you're generating a list of those people, and you are selecting the 10th person off of that. Something like that. I mean, these answers, again, there is no perfect answer. If you wrote something a little bit different from me, I definitely would not want you to rewrite it if you feel good about it. Okay. All right, an observational study. It's in the name. An observational study is where you select a group of people. Maybe you're trying to study sleep habits of doctors in Phoenix, okay? And so you're going to select a group of people, and you are literally going to observe the effects of whatever is happening. So that's why it's observational. You're basically just saying, hey, I'm going to look at this group of people and I'm going to observe what's going on. I am going to observe their sleep habits. I am going to observe what's happening here. Now, when you get into an experiment, this becomes a lot more specific. Now we're talking about two groups. Now we're talking about a control group. That would be a group that is not receiving, the medication or whatever it is. Then an experimental group. And then you are going to give everyone either, let's say the medicine or the placebo, the fake medicine that doesn't actually have anything in it. And then you are going to measure the effects. So let's just I'll say medicine, but you could really there you go. We'll just go with that. And then the effects are measured. There should be an actual experiment taking place where we're not observing, we're actually dividing up into two groups, and we are actually studying the effects, okay? So the difference between an observational study and an experiment, I think you can kind of already see. I'm not going to really write out letter C, but in an observational study, you're just taking a group of people that meet a certain criteria, and you are observing what's happening to them. What are the effects of whatever's going on? Whereas you can see in an experiment, we are being very specific. We have a control group. We have an experimental group. We are giving half of the people one thing and half of the people another thing. We are breaking it down. We are measuring the effects. And so you can see there's a very big difference between the two. All right, so let's go here. Let's look at 31. A pollster surveys 100 people filling up at a gas station about whether or not the city should improve public transportation. Does that not already sound ridiculous to you? It's 100 people filling up at a gas station. If you're filling up at a gas station, chances are you are not using public transportation. Oh my goodness. Okay, so the sample is biased because most of the people at a gas station are not using public transportation. You should be surveying people all over the city. You shouldn't only be surveying people at the gas station, because if I am at a gas station, it is probably to put gas in my car, which is not public transportation. All right, there you go. So it would be like asking Tesla drivers what they think about gas prices. You know, it's just you're surveying one specific group of people that are going to have a very specific opinion about the subject. All right. In a survey of 1,200 teenagers, 48% said they are involved in extracurricular activity. What conclusion can be drawn about the population? Now, this was sort of a trick question. I was expecting to use margin of error here. I was expecting to be like, oh, I'm going to do 1 divided by the square root of 1,200. Okay, there you go. Hey, look, this survey has a 2.9% margin of error. The truth is, I don't think they wanted any of that information. It's kind of good to show here as we do the final exam review, but really all they wanted to say was that about half, or almost half, or 45 to 51% if you include the margin of error of students are in an extracurricular activity. All right, there you go. Yeah, I was expecting there to be a lot more to that question, and there was not. All right, events A and B are independent. All right, so the probability of A, I do not know. The probability of B is 0.3. The probability of both is 0.06. Now, what you should know by now is that if you have two independent events and you want to know the probability of both happening, all you have to do is multiply the probabilities by each other. So that means whatever the probability of A is, multiplied by whatever the probability of B is, should get you the probability of both. Now, I don't actually know the probability of A, so I'm just going to call it X because I can. You can call it whatever you want. So what I would do now, how do you undo multiplying by 0.3? I would divide by 0.3. But whatever you do to one side, you should probably do to the other. So we're going to do that, and we are going to get 0.06 divided by 0.3, also known as 0.2. So the probability of A is 0.2, or 1/5 if you are a fractional person, because we could just take these calculators and we could frac it. All right, there you go. Whew, boy. Okay, so that one came up, I remember, back in the day when we were doing our Chapter 9 tests. So those kinds of problems are not going away. All right, Mitchell discovered he has 125 students in his grade. There are 68 boys, and there are 22 students with green eyes. So all right, now, there are 10 girls with green eyes. So I'm just going to use the magical power of subtraction to recognize that there are now 12 boys with green eyes. It said that he drew a Venn diagram. I am not really sure how a Venn diagram for this one would work. I'm not really thrilled about the way that would break down, so I'm just going to answer the questions based on what I know. How many boys have green eyes? Well, we just figured it out. 12. Okay, there you go. That's your answer to letter A. How many boys do not have green eyes? Well, I suppose what that means is if 12 of them have it, then that means 68 minus 12 would be 56. Okay, there you go. 56 boys do not have green eyes. What is the probability of selecting a male student with green eyes? Okay, so that would be 12 out of 68, because we know 12 of them have it, and there are 68 total. So I'm going to do 12 over 68. That looks like a funky decimal, so I'm going to frac it, which would be 3 out of 17. So I wouldn't leave it as 12 over 68. I would leave it as 3 over 17. Last but not least, what is the probability that a green-eyed student is male? So now we are only looking at the green-eyed students, which are 22. Of those 22, 12 of them are male. So now we would say 12 out of 22. I don't need the calculator to reduce that. I'm just going to call it 6 out of 11 because I just reduced it by 2's. I do not need the calculator to do that one for me. Okay. All right, what is the probability that one of Frida's large marbles is red? So we are on to 35. We're working our way through. There are actually only 6 total large marbles. There are 4 large blue, 2 large red. So what is the probability that one of Frida's large marbles is red? So we're only looking at the large ones. Of the 6, 2 of them are red. 2 out of 6 would reduce to 1/3. I am, again, not using the calculator for that because that is insulting. You've got this. The answer is 1/3. All right, we're moving on here. We're going to get this. Independent or dependent events. All right, a cooler contains 10 bottles of sports drink. You grabbed a bottle, returned it to the cooler, and then mixed up the bottles. You probably shouldn't do that, but it is independent because each draw looked exactly the same. You did not change the contents of the cooler because you grabbed a bottle, you put it back, and then you mixed up the bottles. So each draw was independent. Whereas on B, you've got 15 pieces of chocolate. You grabbed a piece, you ate it. You grabbed a piece, you ate it. You grabbed a piece, you ate it. Every time you grabbed a piece, the total number of chocolates changed. It went from 15 to 14 to 13. So that would be dependent events because your second choice depended on what your first choice was. And your third choice depended on what the first 2 were because you couldn't eat the same chocolate twice. All right, dice are always independent. It's not like you roll the die, you got a 5, and then suddenly you're like, oh, I guess it can't be a 5 anymore. That's not exactly how they work. All right, 8 shirts in your closet, 4 blue and 4 green. You randomly selected one to wear on Monday and then a different one on Tuesday. Your shirt selection on Tuesday depends on what you wore on Monday because you're not going to wear the same shirt twice. All right, 37. I know we're moving quick. Pause it if you need to. Again, dice are independent events, which means you can really just multiply one probability by the other. So the probability of you rolling a 4 is 1 out of 6. Doing it again is 1 out of 6. So overall, it's 1 out of 36. Same thing here. A and B have the same answer because the probability of rolling a 4 is 1 out of 6. The probability of rolling a 3 is 1 out of 6. So you multiply that out, you get 1 out of 36 again. Okay, same exact concept here. I don't know if you noticed this, but it didn't change. The probability of rolling anything is always the same. Probability of rolling a 2 is the same as the probability of rolling a 5. None of these things change. All right, and letter D, same thing. The probability of me rolling a 4, and then rolling a 4, and then rolling a 4 would be 1 out of 216. So A and B were the same, C and D were the same. Okay, pause it if you need to, because we only have 3 more to go, and we're going to go right through. All right. What is the probability of selecting a card that has a letter on it, given that it was green? All right, I love that. We're using the word given now. Now, we've kind of been doing problems like this a few times already, but now they're actually using the word given. Given that it was green. So we know our card is green. So I'm only going to focus on the green ones. Out of the green ones, there are 20. Of those 20, 16 have letters on them. So 16 out of the 20. You could call it 0.8. You could call it 80%. You could call it 4 out of 5. All 3 of these answers would be correct. I believe on the study guide it is listed as 4 out of 5. It doesn't really matter. I want you to be aware that all 3 of these mean the exact same thing. Okay? Whew. Okay, 2 more to go. We got this. We have an OR problem here. The OR situation was the only time I really taught students formulas, and that was because it's kind of like if you were to draw a Venn diagram in an OR situation, you want to make sure you're not counting anything twice. So basically, if you want to know the probability of A or B happening, you have to figure out the first probability, then you have to figure out the second probability, and then you have to subtract the duplicates. Okay. So again, I don't want to spend more than a couple seconds on this, but if you've got a Venn diagram and you're trying to figure out the probability of this or this happening, this middle area gets counted twice, so you have to subtract the middle area because we don't want anything to be counted more than once. Long story short, if 60% of students prefer Desmos and 30% of students prefer a handheld calculator and 10% of students prefer both, you could do 60 plus 30 minus 10, which would be 80%. So again, I'm not huge on probability formulas, but that is one that I think you should probably know. Okay, so Desmos or a graphing calculator. We just don't want that group that used both to be counted twice, so you had to subtract the repeats. All right, last but not least, a drawer contains 10 red socks, 4 white socks, or 6 white socks, 4 blue ones. All right. What is the probability that the first sock is red? Well, that sounds like 10 out of 20. All right, what is the probability the second sock is white? Keep in mind, you put on the first sock. So now there are only 19 in the drawer, and 6 of them are white. Now, I don't want to have to reduce a lot later on, so I am just going to turn the 10 out of 20 into 1/2, because that will just save me a lot of trouble later, so I'm just going to call it 1/2. There you go. 1 times 6 is 6. 2 times 19 is 38. Those are both even numbers, so they reduce to 3 over 19. All right, so I hope that helps you get going for the last part of the final exam. Hopefully you feel good about where you're at. If not, watch it again and again until you feel good about it. Anyway, thanks for watching, and maybe I'll see you next year. Take care.